So thank you for the invitation. It's a great pleasure for me to visit IHAS. So I'm going to give you these 3 lectures on resurgence in integrable field theories. The first 2 lectures will be mostly pedagogical, introducing some of the material needed to go to the point. And then at the very last lecture, the 3rd lecture, there will be some review of new results. Okay. So this is the plan. I was just in the process of writing the plan of the lecture. So in the very first lecture, I decided to give a sort of a quick, after some basic notion, which will be important for the rest of the lectures, basic mathematical notions. Then I'm going to review very quickly the status of Borel and large orders in perturbation theory before resurgence. So if you wish, sort of a overview, very quick overview of history of the last 30, 40 years, streamlined, of course, about what people were supposed to do, what were the aim, what has been found, what has been shown. And I will try to make some sort of a little bit of an emphasis on what has been done in a rigorous way, not much I must say, and what has been done more rigorously. Okay. So this is the plan of the first lecture. So let me now go on writing the plan of the other 2 lectures. So the first lecture is essentially everything before resurgence. So simply sort of historical detour. Then the lecture 2 will start again with some basics, this time basics of resurgence indeed. So so I will take a sort of a pragmatic and more physical approach to this to the subject. Essentially, I will show you in some detail one instance, which is a prototypical instance where you can see most of the interesting phenomena occurring, which is the Airy function. And also, since this is important in quantum field theory, we don't have a generic asymptotic series, but typically the asymptotic series we get come from path integrals, so they are specific asymptotic series. It will be nice to reconnect this resurgence in the Airy function with what is called the steepest descent technique and Lefschetz-Timbal. So I will briefly show to you how essentially algebraic techniques which you can use to solve this problem. This problem is essentially, as you may know, it's a solution of a differential equation, the Airy function. Then you can recast it in writing this solution as an integral, as a Stokes phenomena occurring in this steepest descent phenomena. So Lefschetz-Timbal, and then I will remind you again a bit of, again, very streamlined and very quick. 1 over n expansion, some very basics, the minimum I need for my 3rd lecture about large n expansions. Because we will see in my title of the lectures, it's not written, but we will study integrable field theories also in this 1 over n expansion. So I might want to tell you a few things about what it is, both in vector models and in matrix models. And then finally, again, a quick review on integrable models. Once again, what I need for my lectures. And this is essentially it's a preparatory lecture for the last one. The last one will actually have, yeah, let me write it here. In the last lecture, we will come to the point, so we will compute exactly some observable. So we'll compute the free energy in presence of some chemical potential in some of these integrable models, which I will introduce. And then in particular, I will show to you this computation at in the what is called the principal chiral field. This is a two-dimensional models of essentially of a matrix it's a matrix theory, principal chiral field. This computation will be done at leading order in this 1/n expansion, but it will be done exactly using Bethe ansatz technique. So here it's where integrability comes. Integrability will allow us to do exact computation using the Bethe ansatz. And then, indeed, we will see that if we supposedly we did this computation using perturbation theory, which is very hard, of course, but we can re-extract from the exact result that we got it just the perturbative part, we will see that indeed, using resurgence, we could have reconstructed the result. Okay, so this is, if you wish, this instance is one of the few instances in which you will see how this idea of resurgence works concretely and successfully. Okay, I will show you also other models in the very same approximations, and also some results at finite n. Okay, so these are essentially. So just to go to the point before diving into the details, the key point of my lectures will be the following. So the one I already said, we have it's a beautiful example of a working application of resurgence in a non-topological theories, so to say, or which is still integrable, but at least non-topological, in which many interesting things happen. So this is a theory in which you have spontaneously mass generation, renormalons, which I will introduce it. So it's quite, from a quantum field theory point of view, it's a quite interesting theory. And yet, resurgence will work well. In other models, it's not going to work well. So this is not a general phenomenon. And one of the points we will see is that a large n and these resurgence ideas do not commute. I will spend some time to show you that this was a sort of a specific phenomenon, because here we will be able to compute a planar diagrams to all orders. But in general, in vector models, which are easier, these two limits do not commute. But on the other hand, if you do computation at finite n, this is also possible, although also quite complicated, but they can be done using integrability at finite n. As far as we have been testing as of now, resurgence seems to work. Okay, so this is a bit the point. So the key point here I might want to say is that there has been recent activities in these ideas, using essentially in integrable models as a toy laboratory to understand resurgence, and essentially most of these results I will be based on. I will sort of review on two papers. So one is with Di Pietro, Marigno, and Sbervelieri. So this will be large n. Okay, but then I will also review some other work, not by me, at finite n, so essentially at the very end, by Marigno and Reis. As you see, these are very recent work in which there has been some sort of a progress in understanding how to use these ideas in quantum field theory. Okay, so as I told you, I will try to disentangle what has been done in a sort of a rigorous way, what has been done in a non-rigorous way, which is 90% or more of the material. Okay, so maybe just before actually starting, let me say a few words about references, in case. So just for the very basics on Borel and the Lefschetz symbol, of course there is a vast literature here, most of which is not even on my expertise. So in this case, I just refer to one of my papers. In which you find in a very few pages, I believe, what can be a useful overview without too much, so what you really need, a gentle introduction to these ideas. Then if you want to know more on Lefschetz symbol, but still in a gentle way, without entering into too much mathematics, I will suggest you a paper by Witten. The paper is about Chern-Simons theory, but you don't need to go through the whole paper. Just focus on section 3 of this paper. And again, there will be also a lot of some airy function analysis. Then about resurgence, as of today, there are 2 reviews in the physics community, 1 in the math community, at least the one I know. I might want to point to you all of them. So the first one, in anti-chronological order, it's the by Aniceto, Basar, and Schiappa. So this review is more of an emphasis on physics. It's not very rigorous, but it has the additional bonus of having many examples. It's quite an extensive review with many examples. So if you're really a beginner of these ideas, you might want to look at it because it's the more accessible one. Then we have another review a few years back by Dorigoni. This is more compact, a little bit more math-oriented, so a little bit more rigorous. So if you know a little bit about the subject, you might go for this one. And then we have another one, the first in chronological order, by a mathematician, Sozen, David Sozen. At least for my standard, this is completely systematic and let's say rigorous as much as resurgence can be rigorous, okay? Which I will comment about this, but this is certainly math-oriented, okay? So if you are a mathematician, you might want to go for this directly. And if you are a physicist, better if you go to this if you know a little bit of resurgence already. Okay, so please interrupt me at any time. I will try to be very pedagogical. Maybe if I am even too pedagogical, just tell me we are getting bored, we are getting asleep. Please speed up. Or if there are a few things that you believe I'm not explaining very well, stop me at any time. So questions are always welcome. Okay. Okay, so let's start with the basics. So the basics will be literally basic. So I will just start by reminding you what does it mean for a function to be analytic at a point. So a function f of g is analytic at g0 if in a small disk around the G0, we can have we can expand the function in a Taylor series which is convergent. Okay, so this is a convergent Taylor series. Okay, so this is one possible definition. And the radius of convergence of this series, we can compute it by one of the many methods which are available. For instance, the ratio among coefficients. And in the framework of complex analysis, this radius has a very nice physical interpretation because it's literally the distance between G0 and the first singularity in the complex plane of the function, of the analytic function f of g. So if I have our G plane here, and this is G0, then this is our disk of analyticity. This disk of analyticity stops whenever there is some singularity C or whatever kind of singularities, pole, branch cut, whatsoever. Let's call it a G hat here. And this is our disk.
Okay. Mark, are you sure it's a good formula for the radius?
No, it's not a good formula. Yeah.
It's not a good formula, probably. It's not a good formula?
No.
You should get something like lim sup. Imagine that a series has only second, every second coefficient on zero.
Yes, 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 absolutely. I was a bit.
Cn to the power 1 over n. Or something.
Yeah, I should refine it. Yeah, I was a bit. So lim sup should be enough?
No, not instead of taking the ratio.
Power 1 over n, yeah.
You should take a square root 1 over n of one coefficient. Take C. Instead of taking the ratio Cn over Cn minus 1, you should take just Cn, raise it to the power 1 over n. Yeah, and now take lim sup.
Okay.
And take the inverse.
Minus 1.
Inverse minus 1 over
n.
Yeah, sorry. You see, I thought it was so simple that I got mistaken myself. So yeah, thank you for the correction. So within a disk, the function converges. At the boundary, it depends, as you know, because of the singularity, and beyond the disk, certainly the series is divergent. Okay. So based on this very simple analysis, in 19, sorry, inf, not sup. By the end of the lecture, probably this formula will be correct. Thank you, yes. So in 1952, Dyson, using analyticity argument essentially based on the definition of an analytic function, pointed out that QED, the expansion in QED, perturbation theory in quantum electrodynamics, where alpha, the coupling constant square is the expansion parameter, cannot be convergent. So the analysis is very simple, it will be brief. So Dyson have the idea of looking at observables which are you expand in terms of alpha, and got the idea of going analytic in alpha, so look at alpha as a complex parameter. And then if you look at any observable as a function of alpha, where alpha is supposed to be analytic, he pointed out the following, that if analytic, there should be disk no matter how small. There should be a disk with finite sides in which the function is analytic. Okay. And so if analytic, the observable should make sense also for alpha negative. Of course, for arbitrarily small, but still negative. And then from physical arguments, alpha negative is ruled out, because whatever alpha negative, you have that electron and positron repel each other. You have completely different physics, and you are in a situation in a world in which the vacuum manifestly cannot be stable. You have a huge massive production of electron positron out of the vacuum, and then you should get that any physical observable simply cannot be analytic when you go from positive alpha to negative alpha. So by contradiction, he pointed out that the point alpha equal to 0 must be a non-analytic point, which implies that the series associated cannot be convergent. So this argument was a very brilliant one, as simple as brilliant, and from that point on, we started to think about series in quantum field theory as possibly divergent and not convergent. Okay, so now a modern way of recasting the Dyson argument, which is simply, so just to be a little bit more precise, we will be in a Euclidean space. You consider a correlation function of local operator Gn, so there will be some dependencies on the point which are not of interest for us. The interest will be in the dependent on h bar, and as you know that this can be seen as an integral, a path integral over some fields of the local operators inserted here, and then the exponentials 1 over h bar, some action of phi. Okay, so the
H bar is just a coupling constant here. It's not really the Planck constant.
h bar here is it's the usual h bar, so the h bar can be seen in the loopwise expansion as an expansion for small h bar. It's really literally saddle point. So you expand for small h bar, you do an expansion, and then you see that h bar goes to 0 minus. This term blows up, which is telling you that the loopwise expansion in quantum field theory, without entering in any details for any correlation function of local operators at least, it cannot be analytic. Okay? For the very same reason, essentially Dyson argument recasted in a way in which you see directly the infinity coming from an exponential which blows up is no longer suppressed. Okay? So this is telling you that the usual expansion which we do, which is at around h bar equal to 0, cannot be analytic. And as you know, h bar expansion and coupling constant expansion is the coupling constant is indeed a loopwise coupling constant. They are related, one and the same. You can always do a field redefinition to write an expansion in terms of a coupling which enters as h bar. So in that case, anytime you have an action which is a free action plus a coupling constant times an interaction term, and this g can be absorbed into h, this becomes the usual coupling constant expansions. And then you see that this formula is telling us that, now let me be schematic here, O1, On. So I expand this factor of g here. So this is now no longer written this way, but it's written now this way. Okay? So remove h bar and look at this as g to play the role of h bar. So this becomes e to the minus s naught, sum over p minus g okay. So this is what we have, but then of course written in this way this is not very much useful. What we typically do when we study perturbation theory is to exchange the sum with an integral, and then we study the following. That's what we actually do. Because we are able to compute the Gaussian integral. This is a Gaussian integral. This is something we are able to do. This is a formal writing which we are not, it's useless for us. But this is actually the actual observable of interest. The right-hand side is it's apparently the same things, but I'm exchanging sum and integration. Now it turns out that I cannot change here integration and sums because this is not uniformly convergent. This is a path integral, so understanding what it is, it's very hard mathematically. So even for an ordinary integral, this would not be in general a good allowed operation, even less so for a path integral. So this is not an allowed operation, and then we should not be surprised that this is not equal to this. And this is actually what we get, which is indeed an asymptotic expansion. So from now on, so this I will call it G tilde. G tilde is going to be a formal power series, which has no meaning mathematically speaking, which will be the power series associated with an observable, which is the one without any subscript. Okay, so from now on I will use the following terminology. If you see something with no tilde or anything, it will be some well-defined function. If you see a tilde, this is going to be a formal power series. And then I will introduce other subscript during the lecture later on. Okay, so it's very important from now on that we keep this distinguished, which is a function from its formal asymptotic series. Okay, so so sometimes we will write, so if f is a f of a function of g, we will write these symbols here to say that the function of g, if you expand it, admit a formal power series of this kind. Okay, but the equality sign doesn't work because, literally speaking, for any g, if you compute it, this is simply infinite. Okay. Okay.
And then this is always around g equals 0 when you use the tilde, or it can be around any.
Well, at g equals 0, it is definite. If
yes, no, but just the tilde means.
The tilde means that
0, not around g0.
No, sorry. The tilde simply means it's. I will try to avoid even this symbol here. It simply means that this function admits an asymptotic series as this one. Yeah. Sorry. What was your question?
You will not do expansions around another point g0. No. Everything around the coupling constant 0. Just to.
No, this is a good point. So this is literally applies if you expand around 0. If you expand around a finite point, everything is going to be fine, indeed. So.
But why do you say that f tilde is equal to plus infinity? Because that series doesn't converge, so it may have oscillating coefficients. So why do you know that's plus infinity? Shouldn't you just say that f tilde of g is not defined? It's not a number.
Yeah, I mean. In the example I'm going to, I was going to show you, this is going to grow indefinitely, but yeah, in general, it can be simply not defined. Yes, like you can remove it. Yes. Okay, so as I anticipated that this f tilde here is going to be an asymptotic series. So very quickly, let me remind you what is an asymptotic series. So I hope I will be brief because I don't want to bore you too much. So an asymptotic series is defined to be as a formal power series in which if you take, so this is the truncation of f tilde of g, we write it as a sum, as a formal sum of this kind. If I truncate it at level n minus 1 in this way, and then I take the absolute value, this is in the limit g goes to 0. The residual, the difference between the exact function and this truncated series, has to be of order g to the n. Okay, as g goes to 0. So just contrast this with the usual definition of, hopefully correct, of the convergent series, in which for a convergent series, you see that it's important the emphasis on the fact that this applies in the limit g goes to 0. This applies in the limit in which n goes to infinity in an entire region uniformly. So not only as in the limit, it's at finite g within a disk, of course the disk of convergence, this applies. This only applies at a point, essentially. Okay? So as well known, for convergent series, we have a one-to-one correspondence between a series and its actual function, at least in the domain of convergence. It's a one-to-one. With asymptotic series, it's not one-to-one. Okay? So for asymptotic series, we know that if I have a function f2, which is, let's say, let me give you an instance here, just to show, this is an instance, it's not the most general case. If I have a function f1 which has a asymptotic series f tilde, f2, which is another function of this kind, where a of g is holomorphic and smooth, will have the very same asymptotic expansion, because once you expand, this is going to give you 0, right? So for asymptotic series, there is no way in which, with the asymptotic series, you can reconstruct the actual function in which you start with, because there is not. There is an infinite equivalence classes of function, all of which have the same asymptotic series. Okay? Okay, so let me also now introduce, I think I have to speed up because I think these are things that you should know very well. So again, in terminology, we will, an asymptotic expansion f tilde is said to be algebraic P okay, if the Cn here are bounded in the following way. For some finite k1 and k2 constant. Okay. So in the asymptotic series typically have. Sorry, this is algebraic P if this the value of this coefficient for any n, okay, are bounded by two constants k1 and k2 to the power n. This is n factorial to the power p. Okay. So in all our discussion, we will consider asymptotic series of algebraic 1, okay, because the h bar expansion here, or the coupling constant expansions, always gives rise to algebraic 1 asymptotic series. The precise statement is that the loopwise expansion is algebraic 1. The coupling constant, it's up to you. So whenever the coupling constant expansion indeed is a loopwise expansion, you will get algebraic 1. But if you expand in the square of the coupling or in another power, you will get other algebraic kind of asymptotic series. So since you can always reduce to the case in which your coupling is an h bar a loopwise expansion, we will consider only algebraic 1. Okay?
May I ask you a question?
Yeah, sure.
When you're saying asymptotic series, definition of asymptotic series comes with yet another property that if you truncate a certain number of terms, the error you're making is older than the first neglected term. So there's yet another property which you didn't.
Yeah, this is what I'm not sure this is a definition of the asymptotic series, but this is one of their properties, which I'm going to come next now, right now. So.
But my question is more or less, how do you know that series you're going to deal with the asymptotic one? Where does it come from?
Well, if you wish, at this stage, you don't know. I mean, you only know that you do. If I told you that this is an illegal operation, you know that this is not equal to that. So you don't know. Well, this has been indeed for a long time has been showed up. And in this lecture, I'm hopefully going to review to you all the evidences that we accumulated that show you that this is asymptotic, because we have an estimate. We can have a precise estimate, well, precise, sort of an estimate on how this Cn grows. And we see that, so there are two evidences. One is that in actual physics, if you work at small g, things do work. So this is experimentally verified. So the two things should be related in a regime, because at the end of the day, I'm doing an illegal operation, but I'm computing the very same thing. And on the other hand, we can have some estimate for large values of n. We can estimate this Cn, and we do know that it grows factorially. So if you combine these two, the natural interpretation is that this is an asymptotic series. I don't know if we have any more rigorous and sharper way of looking at, but I would say that this is. I mean, the mathematician here can correct me if I do, if I make a not precise statement. So yeah, as Grisha was introducing, whenever you have an asymptotic series, it's very well known that if you keep computing terms, at some point you do worse and worse, so you should stop at some point, in contrast to convergent series, that the more you know, the better. So if, let's say, Cn goes like n factorial a to the n for n large enough, suppose that when m is big enough, now this is an actual approximation, so it's not the tilde. This is approximately given by this formula here. Okay, so now this is an exercise for you, if you never did it. It's a very simple exercise. So show that if this is the case, then there is an actual, what is called optimal truncation, which means the best number of terms that you should keep in your series to minimize the error. It's actually not fixed. It depends on the value of your coupling constant of G and on this parameter A in the following way. So this means an integer part of the quantity here. And that the error that you do in doing this, so the error, delta n best, and the error is parameterized by minimizing this object here, which is essentially the term Cn g to the n. This goes like e to the minus 1 over ag.
I mean, we can do the exercise, but how is n best defined?
N best is defined is the one which minimizes delta, the error, where this delta is Cn g to the n. So you minimize this quantity, and then you realize that this is the value of n which is minimized, and at the minimum it is of this kind. So this is in fact interesting.
The first n best terms will decrease in the series, and then they will start increasing.
That's right.
And you want to truncate the series when this.
That's right. That's right. That's precisely right. So you see that it's a bit of a counterintuitive, at least to people not working with asymptotic series, that the more the coupling is small, the more it's worth to compute terms. You might say that it's the other way around, right? That if you want to go strong coupling, you need a lot of terms. Well, this is true in the convergent series, but for the divergent series, the more only when the coupling is small, it's worth to compute many terms, because you see that this n best grows when G is small. If G is not so big, just keep a very few terms, and you will get a more reliable estimate of your quantity. Okay? So this is the reasons of the success of quantum field theory in the actual world. So most, as you know, quantum field theory, the standard model is based on perturbative physics. Most of the computation are done using a perturbation theory, which I just told you that mathematically speaking do not make any sense. Okay? But what comes at the rescue at the end is that the error that you make, if G is alpha in the actual world in QED is 1 over 137. A nobody knows, surprisingly enough, but it's expected to be a number of order 1. So you see that unless you compute more than 140 loops, you are going to be fine with this asymptotic series. So the problem is only, for QED at least, it's only mathematically, just how to define things. It's not a problem at any practical level whatsoever. In QCD, things are a bit more different, because of course, if you have a strong coupling, generic strongly coupled theories, then all this has also a practical interest, because clearly you have to deal with this series. Okay? So indeed, what do you do if G is not a small number, but it's a large number, which means that n best is of order 1. So there is no information that you can get from this process. And then you may say, okay, just I give up, I do some other, I do something else. Well, before doing something else, what you can do, you can...
Marco, I have a question.
Yes.
I asked you about the sign in this error estimate, the sign of the exponent. I think it should be minus.
It's minus, yeah, sorry. I mean, yeah, sorry, it wasn't very clearly written. It's minus, yeah. No, otherwise it will be a disaster. It's minus, yes, sorry. Okay. So, of course, what we can do, we can try to resum series.
Sorry, can I ask, is this the same order that the larger asymptotics are kicking in, right?
This one?
Yeah, this n best would also be, when you actually do perturbation calculation, this n best would be the order at which your coefficient starts to look like this n factorial.
Not necessarily. For instance, I can give you a very stupid example. If you take just mathematical, you take a series in which this is exactly of this kind, okay, then this formula applies for any n, and yet you get the estimate of this kind. So the estimate and when the asymptotic starts are in principle independent object. Okay.
And there's no good way to determine that.
There is not a simple way to determine when your actual coefficients start to be asymptotic, yes. At least as far as I know. Okay.
Yeah, I'm confused by it. You're saying it's the n where you minimize
Yes.
C and G.
Minimize this quantity delta n here. You minimize this quantity here, and you minimize in n. At fixed G, you minimize in n. Essentially, you have to use Stirling formula. It's a very simple exercise. It's a very simple, and you minimize in n, and you find this this number. Okay. So, what we can do is, at least we can try, is Borel summation. So now let me introduce once and for all another symbol. So given f tilde, which is, remember, it's the asymptotic formal series, you can define f hat of g, which is simply the formal, no longer formal now, series in which you simply divide by, sorry, f hat of t. Let's change name. Okay. So I call it T because at some point there will be the plane of the physical interest, the Coupling constant plane G, and then there will be the so-called the Borel plane T. So that's why it's useful to keep two different parameters. So this is called the Borel transforms of the function f. Okay, it's constructed in terms of the coefficient of f tilde. And now you see that by construction, if Cn is Gevrey 1, this u divided by n factorial, f hat is necessarily analytic at the origin by construction. So this is now analytic at t equal to 0. And generically, the radius of convergence of this series is finite. It has to be finite because the Cn were n factorial, and which means that asymptotically this f hat is a power series. And as you know, a power series typically has singularities at finite value in the complex plane. And this is important, okay? So if you take a series, let's say, that was already convergent to start with, and you make a Borel transformation, you don't do a good job to you, because you will get an ultra-convergent series which becomes an exponential, which might be problematic in terms of integration. It's might not longer be L2 integrable or things like that. Okay, so it's very important that you divide, you don't over-divide. Okay, so if it is Gevrey 1, you divide by n factorial. For a Gevrey p, you will have divided by n factorial to the power p. Okay, that's what you are supposed to do, so that the function that you get, it's a smooth function with around a neighborhood of the origin, and then has some singularities all over the plane.
I actually didn't understand. What's the problem if you over-divide?
If you over-divide, you will have a behavior at infinity which is too wild. Typically, you will have an exponential behavior at infinity.
But you may get this behavior even if you under-divide.
No, if you under-divide, it's a disaster, because if you under-divide, under-division, I didn't emphasize because it's obviously not enough. If you under-divide, the series is still divergent asymptotic, so you don't do nothing. I was emphasizing the other regime, which is less obvious, if you over-divide. Okay. Anyhow, yeah, let me.
You say you don't want this function to be entire analytic.
I don't want this function to be entire analytic. Yes, because otherwise at infinity it will have a not so good behavior. I want to do my enough what I need, and then from this you can define the Borel transforms, which I will denote with an S as an operation as S acting on f tilde. This is just a definition here. This is simply the Laplace transform of this. So the integral from 0 to infinity in dt, e to the minus t, f tilde of gt. Okay? So this is called the Borel sum of the asymptotic series f tilde. So under some condition, this integral is finite and gives you back, out of a formal asymptotic series, produces for you a well-defined function. So just to show you that indeed this function, if I expand it, gives me back f tilde, you can simply plug this formula here. So let's do this. Okay. Now again, I bring this outside. This is going to be wrong. Okay. Again, I will tell you, well, it's obviously why, but let's do this anyhow. but this integral, you know, this is precisely the gamma function over n factorial. This gives you 1, and then this is exactly which is exactly f tilde of g. So fb, if expanded for small g, gives you back f tilde of g. So it has a good asymptotic expansion. Now, of course, I mean, fb is supposed to be a well-defined function. So this is a formal object. So where is the mistake? The mistake is again in exchanging sum of integration. So this I told you has a finite radius of convergence in general. But here I'm supposed to integrate from 0 to infinity. This cannot be uniformly convergent. You remember that in order to exchange sum of integration, you need uniform convergence. You never have uniform convergence over the entire axis here, so you are not allowed to do this operation. This illegal operation, you insist in doing it, so you do a mistake, but the mistake is simply to turn your actual function in an asymptotic, precisely as we did it for the path integral before. So here it's the sin that you do that makes the function an asymptotic series, but aside from that, you reproduces the correct asymptotic series. So fb is a good candidate to give you the actual function, because it has at least the very same asymptotic series. But I just told you that infinite number of functions have the very same asymptotic series. So now the quick question is fb equal to f? The answer is non-trivial indeed, and so the final answer is it depends, and there are some conditions for which this is true, which I'm going to review here very quickly. So the best, at least to me, the strongest results available are due to Nevan linear. A linear theorem, which apparently it has been to some extent forgotten, and then it has been rediscovered by Sokal in 1980. So this is more than a century old, this theorem, and apparently, I say apparently because I'm not really a mathematician, so I don't know the literature enough. Yeah, it has been rediscovered by Sokal. So yeah, I will try to be brief because I'm running out of time. I think I'm going very, very slow. So the theorem is the following. So if f, so in order to be so-called Borel resummable, f has to have a specific analyticity property. The analyticity property are the following. So f should be analytic in a disk. So we know that at 0 is not analytic, right? Because we know that it's around 0 gives you an asymptotic series. So certainly the 0 is a non-analytic point, but then you have to assume that the 0 is just the boundary of a convergent region, which means that the series, the function converges in a radius, in a disk of radius r. So this is a radius r, and it's analytic here. So this is the minimum analyticity domain of the function g. So the function has to be analytic here. So the origin is at the boundary of the analyticity domain. Of course, it's not included. It's in the closure of this disk. But it has to be analytic within the open disk of this kind. R is whatever. Okay. And then if f is analytic within this disk, and in that disk it admits a Gevrey-1 asymptotic series expansion. Sorry, the asymptotic series is in Fg, but then if sorry, I didn't express. So I'm rewriting in a slightly different form what I already showed to you before, which is the definition of a Gevrey-1 series. Okay, but in that
is a condition on f tilde or on f?
This is the condition, since this is a formal power series, on the asymptotic series of f. So f has an asymptotic series which I denoted by f tilde. Yeah. Well,
Now, why you're writing the condition on Rn of G for Hg?
sorry, this is no. Indeed, I was wrong. So this is the expansion at 0. Fg has an expansion at 0, which is f tilde of g, and then f tilde of g has admit this.
But tilde makes no sense as a function. It's a full power series. So you cannot write inequalities for f.
Yeah, sorry, I think you are right. So, yeah, I'm sorry. So f tilde, yeah, sorry. Yeah, sorry. F tilde is this formal power series. Here, in order to have a well-defined function, I truncate it, and then I call this the residual. So this is well-defined as a function because it's a truncated series. Yeah, thank you for the, I got confused. So then the condition is that if this residual here is satisfied this Gevrey condition within the disk, this disk of analyticity, then, and only if these conditions are satisfied, Fb, which is the Borel resummation of this f tilde, of the f tilde, is equal to f. In particular, you can show that in the t-plane.
But shouldn't there be some relation between R and K2?
Yeah. There is a relation about, yeah. So in the Borel transforms of f, which we call it f hat, if these conditions are realized, it's analytic in a strip-like region of this kind, including the whole positive axis, which is the one where you are supposed to integrate. And the strip-like region here is of the 1 over K2, so it depends on the coefficient K2 here. Where is it? Here. And the R enter in saying that what you can prove is that in this strip-like region, the modulus of the Borel function is less than a function divided by R. So R enters here. But of course, the theorem does not tell you R. R is, of course, depends on the problem you have. So this is the theorem. Okay. So under this condition, this is if and only if. So also vice versa is true. So under this condition, we are assured that the Borel resummation actually reproduces the function. When this is the case, we see that an asymptotic series is Borel resummable to the exact result. Because even if you are Borel resummable, you might be not sure that you are missing some other piece, but if the conditions are satisfied, this theorem guarantees that nothing is lost. Now, unfortunately,
if and only if, because if it's if and only if, then the theorem should tell you what R is.
No, the theorem does not tell you what R is, right? Because if I don't remember in the proof in the converse what you do, but you don't need to spin. It is not going to tell you what R is. Yeah. So this is a very nice result, also because it's sharp and if and only if. Unfortunately, in actual situations, it's very hard to prove the analyticity condition of your starting function. I mean, the starting function is, of course, your unknown. Most of the situation is we do all this perturbation theorem business because we have no idea on how to treat it. So knowing this analyticity property is typically a luxury that we don't have. So unfortunately, despite this nice theorem, there are a few cases in which we can actually use it. Okay? But nevertheless, I wanted to give you this theorem because it's an important piece of info in this kind of business. And now let me just give you another little exercise. So you may know that the typical function which is used, so this is an exercise. So suppose I have a function f of z, which is of the kind exp e to the minus z to the minus alpha. And let's take alpha bigger than 1. So as we said, if you try to do an expansion around the origin of this function, well, at the origin there is an essential singularities, you get simply 0, right? And nevertheless, this function is analytic in any disk, because aside from the essential singularity at 0, this is analytic everywhere outside the origin. So the question is, something goes wrong, because the asymptotic series gives 0. If I Borel sum it, I will get the function 0. So this theorem does not apply. So the exercise is to show you that indeed this is a good, I mean, it's very useful, this exercise, because it shows you that what is not going to apply is this condition here does not hold. So show that there exists a curve in the disk, in this disk R, where condition star does not apply. So just to show you also that this condition is also very important. Okay. Okay. So another point of basic info. I defined the Borel by dividing by n factorial, but in principle I could have divided by some other factorial. In particular, there is an entire one parameter family of division that I could do within the Gevrey one. So Gevrey one tells me that it should be factorial, but the precise detail of which factorial it's up to me. So for instance, instead of n factorial, I could have written n plus 1 plus b, where b is an arbitrary real parameter. So of course the previous case was b equal to 0, which is the ordinary Borel function. But if I introduce a non-trivial b, nothing really changes. The only change is that due to this factor here, the inverse transformation now requires, I mean, this is just another very simple exercise, that with this b here, you recover the correct formal power series by adding t to the b here. So this is now the correct Borel. But the important point is to show you that even the Borel function, given a function f, the actual form of the Borel function can change, because you can divide the Borel you can define the Borel function using a parameter, and depending on the parameter, actually you might wonder whether the singularity of the function might change. Now, this is the only piece of information that I give you. The location of the singularity of the Borel function of f hat do not change if you change b. This can be proved relatively easily. But what can change is the nature of the singularities. So depending on b, you can have that at the given point, which is fixed, it cannot move, the singularity is a branch cut of some kind, or can be a branch cut of another kind, or it can be a log singularity. It can become, it can change its nature. Okay? But the location is fixed. So the position of singularities are fixed under this operation here.
And the function, the Borel transform, hb of g, does it depend on small b?
fb of g is always the same. Yeah. Okay, just to give you some familiarity, and then please tell me when at some point we want to have a break. Let me just show you, if you never have seen any Borel function, let me show you the very simplest cases. So the very simple one, to give you the familiarity, is the one in which the coefficients Cn are exactly equal to n factorial a to the n. So this is not an asymptotic form, it's precisely like this. So with a real, now it's in a minute you realize that, well actually in a second you realize that the Borel function in this case is easily computed. You get this function here. And now you immediately see that there is a pole, a simple pole in this case. So we have a pole at t equal 1 over a. Now you see that there are two cases in this very simple instance. So if a is positive, the pole is in the positive real axis, and this is the region in which I'm supposed to integrate to get back my function. So this is a bad situation. So this is the situation in which it's not Borel resummable. It does not satisfy Neval-Linear theorem, because in this strip-like region that you can still hopefully see, this is not analytic because there is a pole here. Okay? So this is the case in which we say this is not Borel resummable. there is an ambiguity. If A is less than 0, in this particular case, this is actually Borel resummable. In this particular case, we see by naked eye that the Nevalinha conditions of the Borel are satisfied. This is completely analytic everywhere. Aside
to check Nevalinha theorem, you have to exhibit first this function H.
No, but the converse, I mean, you can show this trivially, that in this strip-like, it's analytic, because you have the full Borel function in front of your eyes, so you know that this is analytic over this entire strip-like region here. So in this case, this is Borel resummable. So you see what is the difference between these two cases. In one case, the coefficients do not alternate in sign. In the other case, they do alternate in sign. So this comes, this very simple instance is at the base of a sort of a common law among physicists that same sign series are not Borel resummable, alternating sides are Borel resummable. So this is, I mean, this particular case, it's obviously true, but in general, this is just I want to emphasize to you that this is a sort of a law, because in the more generic situation in which this is only asymptotic formula, this gives you the pole of the closed singularity at the origin, but then you need analyticity over the entire strip-like region, and nobody guarantees to you that you have a singularity here on the positive real axis, which is not the closest one. So having a asymptotically alternating sides is not good enough to show you Borel summability. Okay? While in contrast, if you have same sign series, typically this is enough to tell you that indeed you have a problem. Okay? So yeah, maybe just a last little piece, which will be at the basis of all our consideration. So whenever you are not Borel resummable, you see that there is an ambiguity. This ambiguity is going to play an important role in the lectures that follows. So in the T-plane, so if this is the point 1 over A, I am supposed to integrate, then well, a way to avoid the pole here is to slightly deform the contour, and you can go either up or down. So what I can call it C plus or C minus. I infinitesimally deform the contour. But then you see that, of course, I get two different answers if I do the integration plus or integration minus. So this I will call it S plus and S minus. So the integration along an infinitesimal rotation of angle epsilon with respect to the real axis. And you see that the difference between the two transformations here, it's in this specific simple case, pick up precisely the residue of this pole, and you see by applying the residue theorem, this is give you e to the minus 1 over ag, which is, by the way, precisely the indeterminacy that we have seen generically on asymptotic series. So you see that any time that there are singularities here, there is an ambiguity that you should somehow deal with, because you are not Borel resummable of this kind. Okay, so maybe we can have a break and then keep going after. Okay, so thank you for still attending. So yeah, let me tell you a few comments about what has been the use of all this in quantum field theory since, say, the last 10 years or so, 15 years or so, which means before resurgence techniques somehow came out. So the emphasis at the very early stages of quantum field theory was on having Borel resummable functions, so Borel resummable series. So if something was not Borel resummable, you just give up. Okay? So this was the first emphasis, because there was no idea how to deal with the non-Borel resummable function. So this was the aim, looking for theories in which somehow you can prove in a way or another that the asymptotic series is Borel resummable. Now, it turns out that in quantum field theory, it's very few, unfortunately, very few asymptotic series are indeed Borel resummable, but at least they exist. So the classic series of theories in which, and actually among the very few that have been proved to be Borel resummable by an appropriate studies of Schwinger functions analyticity, so where one could have been proving the existence of this disk in Nevalinha theorem, it's essentially the bosonic theories. So with quartic scalar interactions. Essentially the family of the 5 to the 4 theories. So the proof has been found for this kind of theories. Not in D equal to 4, no. So, okay, in D equal to 0, this is something we are going to show at some point, well, in a few minutes, which is just an ordinary integral. Then in D equal to 1, this is a well-known, this is one of the most known example. The large order behavior has been shown in the late 60s by Bender and Wu in some classic papers in the what is called the anharmonic oscillator, which is the reduction of these theories to one dimension, the quantum anharmonic oscillator. The summability has been proven by Leff et al., Whiteman, Simon, and Dyson in the 69 and 70. The formal rigorous proof of Borel summability of the series in the anharmonic oscillator. So here we are talking about the series in H bar for the energy levels of a bounded system. Okay, so this is the observable we are talking about, the energy levels as a function of H bar if you compute in perturbation theory. Then in D equal to 2, so just let me write to short it, just the years in which this has been proved. I'm sorry for the authors here. And this I believe since probably Stokes, I don't know really. So in a few letters after, the 5 to the 4 quantum field theory in 2 dimensions, okay, in the unbroken phase, okay, with the positive mass, in the disordered phase, so to say, this has been proven to have an asymptotic series, which is indeed a Borel resummable, and in 3 dimensions as well. There are a little bit of a caveats, I believe, in this proof, but essentially it applies. Now there are a few details in which I will not enter. So these proofs, when we are talking about quantum field theories, formally applies in specific renormalization schemes, because in quantum field theory, you know, there are UV divergences that you have to take care of, and you have to pay attention to this. So all the proofs rely on specific renormalization schemes. So whether the series is always Borel resummable in any other renormalization scheme is not clear, and also if in the more standard renormalization scheme it is still not completely settled. But anyhow, there exists at least a renormalization scheme in which people proved the Borel resummability of this theories.
Excuse me. So you literally just set the coupling for 5 to the 6 to 0 in this case, in all the higher powers to 0, even
5 to the 6.
Yeah, 5 to the 6 you set the coupling to 0 in this case, and then you prove.
Yeah, well, in fact, I didn't want to enter into this because of lack of time. So this is a subclass of theories in which Borel summability has been proven. As a matter of fact, in D equal to 2, this is a generic P of phi with some few conditions on the potential, just to be more precise. So you don't have to have degenerate vacua, but if you can have an arbitrary potential. But I just wanted to show you a subclass of theory. This is not exhaustive. There are other theories in which Borel summability has been proven. This is simply a notable subclass of theories in which summability has been proven.
What about 3? It's also for general P?
No, for 3 is actually 5 to the 4, because with the 6 there will be another issue, which is renormalon singularities. We are going to discuss hopefully at the end of this lecture. Okay.
When you see this, like, what observable do you think, or like any observable?
Yeah, also here. So the observable in which they have been studying are smeared version of Schwinger functions. So you have a correlation function of local operators. They depend on x. You smear with some test functions. So at the end of the day, they become a function of decoupling. And this function of decoupling, the analyticity structure has been studied, and the rest follows. Okay, so given this, so people were happy, and then we say, okay, now let's now that we know that we can Borel sum, let's try to compute as many times as we can, and then we attempt to do some numerical estimate of the Borel. So this was the idea. But in order to do that, it's very useful to know something more. So not only that the series is Borel summable, but it actually turns out to be good also for numerical precision, for numerical practical reasons, to know more about the behavior of the series. So a lot of emphasis has been played along the years in understanding what is the precise form of this Cn when n is large. What is the asymptotic or large order behavior? So indeed, in the early days in quantum field theory of large order behavior, most of the emphasis was in understanding what are essentially two numbers, which is the one I introduced already, this A, and also, which is also less interesting but still important, this subleading correction, this coefficient C. Okay, and again, the reason is once you know this, this is going to help you in if you have a finite number of terms. So if I have a finite number of terms, of course, as you know, I cannot integrate term by term the Borel because I go back to my asymptotic series. This doesn't make any sense. So if I have a finite number of terms, I have to estimate the actual finite Borel function with some numerical methods. And here it turned out that if you know this A, you can apply some good methods, conformal mapping, for instance, with some assumption the singularities or other methods. So I don't have time to enter into this business of numerical business, which is also interesting, but just to give you the motivation why people were interested to this. Okay. Now, in the context of quantum field theory, there was a very nice trick introduced by Lipatov in '77, which is a nice trick, which is not rigorous at all, but at the end of the day, it works, and its actual proof requires resurgence. So we are going to discuss it in some way or another in next week. So let me just give you the trick, okay? So there is a trick. I call it trick, okay? Because due to Lipatov in '77 to estimate the large order behavior. Okay, so just to give you the idea, let's estimate using this trick the large order behavior of the zero-dimensional integral. Okay, so the zero-dimensional integral so this is this integral here. It's a function of g. I mean, you can easily see with a simple computation that if you expand it, this is an asymptotic series, and then this is what I call it the I tilde of g, this formal series here. In here, it's obviously by direct computation, you compute in a second the actual exact form of this coefficient here, which I give you here. Which for large n approximate to n factorial minus 4 to the n square root of pi n to the minus 1, 1 plus order 1 over n. Okay? So now here, of course, we know the result, but let's see how we can get this result using this Lipatov's trick. So Lipatov's trick is essentially, it's very simple. It's to use saddle point approximations in a combined integral. So you see that it's based on a sort of illegal step, which however does not affect the result. If I look at this expression as a formal power series, you see that I can reproduce a Cn by taking a contour integral in G. If I do this contour around a small this gives me, by definition, Cn, right? If I do a small contour around g equal to 0, just a residue theorem. With 2 pi I, yes. Thank you. Okay. So now the trick is that I illegally, so to say, substitute in this formula, instead of I tilde, I actually put I, the full function, rewritten in this form. I mean, this is illegal, but as long as you are estimating the large order behavior of a formal power series, it's perfectly legitimate. So mathematically it does not make any sense, but since you are estimating the coefficient of something that does not make any sense, which is a formal power series, this mistake does not result in any actual mistake in your computation. So this is, that's why I call it the trick. So you do this replacement here, And now what you do, you have a couple of integrals, and you can estimate this integral by using a saddle point for both of them at the same time. Okay? So this is not difficult to do. It's good to, however, to do together. So you see that if n is big and g is small, if I rescale x with the square root of g of y, this becomes of the form 1 over g multiplying everything here. And then for g small and n large, I can use saddle point approximation for both integrals. Okay? So essentially, we have to estimate the following integral here, integral in dg, integral in some integral in dz. So z is the integral in y. In saddle point, of course, you go complex, and then you look for saddles. So this is the analytic continuation of the dy integral here. And then we have e to the minus 1 over g, z square over 2 plus z4 over 4, minus n plus 3/2 log of g. Okay? So using saddle point, simply to do derivatives, so we can do this immediately. So you see that if I minimize in z, I get 3 saddle points, z equal to 0 and z equal plus or minus I. And if I minimize in g, I get 1 over g square, z square over 2 plus z4 over 4, minus n plus 3/2 1 over g equal to 0. So these are the systems that I get. And then you see that when z is equal to 0, the only solution of the other equation is g equal to infinity. So here I have an infinite action, so this is excluded. It's not a good solution. But then I have the other two saddles, plus or minus I. And this, in these saddles, this is finite. And G has also a saddle point, which is minus 1 over 4 n plus 3/2. And this is good to see that my saddle is for when n is large, G0 is very small, which means that we are in the good situation where saddle point approximation works well. Okay, so it's good that we have. Now what you do, as usual in the saddle point, the leading order approximation, you plug this result back into your action. Okay, and if you do that, what do we get? We get exp of minus n plus 3/2 minus n plus 3/2 log of minus 4 n plus 3/2 to the minus 1. Okay, and now if you now we are at very large n, so forget this 3/2 here. You see you can see immediately that this gives you n factorial minus 4 to the n, which reproduces indeed the n factorial minus 4 to the n. Now, if you do a little bit of a more careful computation, as you know, in the saddle point approximation, you have to also integrate around the quantum fluctuation, the one loop, so to say. If you do that, I'm not going to do this, you would reproduce also this n to the minus 1, and actually even the square root of pi. Okay? So it's obvious that you can use the very same technique now also with path integrals, and this trick here opened the way at that time to do computation of... Sorry?
Is it hard to make this rigorous?
No, I mean at least for ordinary integrals. For ordinary integrals, yeah, I don't have time to enter into this. So for ordinary integrals, there is a very nice way to make it rigorous by Berry and Olds, Michael Berry and Olds, using indeed what we would say resurgence. So what you do, you take the integral, you do saddle point, and then you start to rotate your contour. At some point you meet another saddle, and then you realize that the large order behavior of a saddle is given by the lowest order behavior of a nearby saddle. This is, I'm going to show you the formula, and this is going to be rigorous, yes. This is at the basis indeed of what we are going to do, yes.
But what about, it seems to me like if you take million bars representation with this exponential factor, you could different way to do the calculation. But imagine I take as exponential factor, exponential minus g, etc., write million bars representation, like integral parallel to the imaginary axis of the power of g. And then you could do the calculation analytically, and finally you get to the integral on the complex plane of some function which had exactly the same saddle points. And these are, there is no caveat on the calculation.
Yeah, I mean, just to make it clear, this computation can be done in many, many ways, and some of which, if you assume that you know that there is the non-analyticity, for instance, in some specific region, for instance, here you might argue that this I of G has only singularity at the origin and then a branch cut for negative real values, which is indeed the case. Then you can do some sort of dispersion relation starting from an arbitrary point with a contour, with the usual contour, blow up the contour. It's a sort of unitarity game, and then the imaginary, the discontinuity will give you, you can do this computation in many, many ways. Yeah, perfect. This is just the simplest Lipatov original trick.
And then there is another statement from Lipatov that actually every time you have some non-trivial classical solution, so you have this integral, I could promote the exponent to some classical action. As soon as the classical action has a non-trivial classical solution, it should
yeah, this is not correct, in fact, in general. This is not correct, because indeed one of the points of Lefschetz-Tinbol descent, the steepest descent, and the resurgence indeed shown is that not every saddles contribute. So understanding which saddles contribute, which do not, it's something which requires a little bit of attention. So here in this case it's so simple that there are only two other saddles, they both contribute, plus I minus I. So the issue is not really visible, but in the path integral, in the full field theory the analysis is more complicated. I will come to this in a second. Yes. So yes.
I mean, speaking. So you say making things rigorous. You talked about the saddle point approximation mostly, but is it obvious that rigorously Cn is given by this contour integral?
Yeah, if you give me a few seconds, I'm going to show you the full formula by, indeed now, I'm going to show you an exact formula that has been found by Bethe and Knowles. Maybe it was already known in the mathematical literature, but apparently this is the way in which. So, yeah, let me go directly to the way to formalize. So, at least for ordinary integrals, it's not a big deal to show how to make this precise. So let me state it for you. So for ordinary integrals, if I have an integral of this kind, where now 0 means around some arbitrary saddle point z0, okay? And also let me be a bit more precise on the normalization to have things which are single valued. So I don't want to spend too much time in this, but let me at least tell you. So suppose that you have an integral which is already in the steepest, C0 is already the good steepest descent path associated with the saddle point at Z0. So in contrast to that case in which I had to deform it to find the actual steepest descent contour, let's just for simplicity to consider that I am already in the good steepest descent contour. So in this situation here, so Z0 then is the saddle, it's one of the saddle of F, namely F prime at Z0 is equal to 0. Okay. Then the formula, the precise formula, I mean there is a formula, a full formula for the actual CP at finite, which I'm not going to report to you because we will go too much time to enter into all this. So I may write that formula in the limit where P is large. Then the formula becomes, this is the general rigorous formula. So let me explain here. So Z0 is the original saddle point that you want to integrate over. Okay. Zn are the nearby saddle points of Z0. Now, what precisely nearby means, I don't have time to explain. So these are the one with the less distance, where the distance is given by this difference here. So this is the function evaluated at one saddle, the nearby saddles minus this one. This is, when this is the smallest, this gives you the biggest contribution here. Okay, not all the nearby contribute to the one where some Stokes phenomenon appears. So we will discuss Stokes phenomenon in the second lecture, so let me just avoid this. In simple situation, typically these are literally the closest saddles to Z0. And then this is the full formula. Gamma of P is just the gamma function, so this is P minus 1 factorial here, and this is it, okay? And C0n, what is? This is the leading order contribution. As you see, this is the usual saddle point approximation, but for the nearby saddle.
Yeah, but this is very confusing. Why should I care about nearby saddle?
This is the point, as you see from here.
Here it was not clear.
Well, you see here, we were looking at an integral which was over the reals, and over the reals you actually already end up in hitting only the origin as a good saddle. You don't need to do, you see, the original integral I was talking about, z equal to 0, was the actual contributing saddle point. Now we were looking to the large order.
Because there was no saddle in G.
No, wait. There is we should not confuse the saddle contributing to your observable. The observable was supposed to be this one, over the real, and this one. Okay, so in order to compute the integral, if you want to estimate the integral, not the large order behavior, forget the large order behavior, G equal to x equal to 0 is the only saddle point, because I actually already encountered in my contour, I don't need to deform anything. G x equal to 0 is the good saddle point to estimate I. Now there is another sort of auxiliary integral, which is the integral I have to do to estimate the large order behavior. So this is an independent computation. In here, actually it's the other way around. My original saddle does not count, because indeed it will give me an infinite contribution. It's the nearby saddles that enter. The nearby saddles do not enter in the evaluation of the actual function, but they do enter in the evaluation of the large order behavior of the coefficient.
Okay, suppose that now I take a contour which passes through the saddle z equals I. Should I then care to do this computation about the other saddles, z equal minus? Why? Is it not obvious?
Yeah. Well, if you want to know the large order behavior of the series at around z equal to I, you have to look at the saddles at z equal to 0, which is the other way around with respect to this one. Yes. And this is summarized in this very nice formula. So given a saddle point, the large order behavior around the saddle is given by the leading coefficient, indeed the very leading coefficient of the nearby saddles. And indeed there's another little exercise. Just show, using this formula here, show that apply this formula to that formula and show that you perfectly reproduce the behavior that I deleted here. Show that star reproduces exactly the behavior, which means with all the minus 1 square root of pi. So this is indeed it's the very first encountering of resurgence in the sense of different saddle points talking with each other. Okay. Now, again, before this relatively more new approach, the Lipatov, let me call it the Lipatov trick, has been used a lot. And also, let me now just give you a very simple instance of application in quantum mechanics, very quick, just to show you how relatively easy it would be for simple theories to apply this nice trick. Sorry? Oh, yes. So let me just show to you very quickly how to, in the anharmonic potential, quartic anharmonic potential, you could estimate the large order behavior of the ground state energy. So E0 is the ground state energy. This admits its formal power series the usual way, some En G to the n, and we want to estimate the coefficient En. Sorry, I call it Cn. So I will be more schematic here, just because lack of time. So you do the integral over G, the usual integral, which is supposed to be around a closed contour around the origin. Then you do a path integral in Q, e to the minus n log of G. It will be plus 1 or plus whatever, but I mean, let's keep it the leading order for large n. And then here we have a minus 1 over G, and then the integral from minus infinity to plus infinity in dt of the usual Lagrangian for the anharmonic oscillator. So q dot square plus q square over 2 plus q to the 4 over 4, where the G I redefined Q as usual to have a loopwise expansion. And now here the saddle points.
Why is this extracting energy, ground state energy? Should take some log of the partition function, I understand.
Yeah. I mean, this is good to provide to you the partition function. Yeah. The larger the behavior of the partition function, since from the partition function with the suitable limits you get immediately the ground state energy. So this automatically give you all the procedure to get the ground state energy are stable. The larger the behavior is the same. Yeah. So again, we use you minimize with respect to Q, with respect to G. So with respect to Q, this is nothing else than the equation of motion. With respect to G, this is what? It's minus n over G plus 1 over G square, and then let's say S0, which is this action evaluated at this other fixed point, equal to 0. Remember that Q now has to be over the complex, because as here we extended the original contour into the complex plane, here similarly the path integral in Q starts as classical trajectories, but now you have to go complex, because we have to find the configuration, the finite action configuration, which are, say, nearby to our saddle. So we have to go complex in Q, which means that we have to look for solutions also with complex solutions. Okay, with finite action, however, because if it is infinite action, they of course they do not contribute. You get a 0 here, and in this case, it's actually very easy. So the solution that you get, it's a purely imaginary instantons of this kind. You can just show very easily that this 1 over cos function here satisfies the equation of motion, and that's a finite action. If you plug into the action, you get that S0 is equal to minus 4 over 3. You plug it, of course, there is also G0. G0 is given by this formula here. Okay, G0 is this number over n. You plug it here back, and then you get that Cn goes like n factorial S0 to the power minus n, which means essentially minus 3/4 to the power n. So you see that with a very simple exercise, we found the large order behavior and also this alternating sign, which, as we know, is a first indication of a Borel summability. In this case, as I told you, you can rigorously prove that indeed this series is Borel summable. Now,
and also this asymptotic is good.
This asymptotic is good, yes. Well, you can refine it, and Bender-Wu did a much better work, but just to go to the point, so for ordinary integrals and one-dimensional path integrals, quantum mechanics, we have rigorous results. Yes.
And also this behavior in this case is one-to-one correspondence with the existence of the instanton.
Yes, it is. Yes, complex instantons. These are complex. Okay.
It depends how. It depends how you coupling. It's question of how you're writing the integral.
Yeah.
Because I think the scale coupling constant x, so the coupling constant will be in front of the G force.
Yeah, but it's important because you see that actual instantons, I mean instantons that when you compute an observable, you are supposed to consider, like in the case before, right? You have other saddles, should we include it? In this situation, the actual observable, and not the trick to compute the larger the behavior, doesn't require any instanton. Indeed, in the actual observable, since it's a purely convex potential, there are no instantons whatsoever. In the purely anharmonic with a positive mass like here.
No, but if I change G to minus G, I will have double wall potential.
Change G to minus G, you do. Yeah, sure. Yeah, sorry. Over the real physical situation for positive coupling and positive mass, This system doesn't have any instanton.
True, but on the other side, since you've got standard magnetic series, this singularity is not, Borel singularity is not dangerous.
Yes.
Right? The dangerous will appear when you go to negative.
Yeah, indeed, yes.
And instantons is one-to-one correspondence with the existence of Borel singularities.
Yes, but the point I want to make is that independently of whether the observable, original observable, requires instantons or not, the observable, in this case, does not. In order to determine the large order behavior, since in order to do that you have to go complex, you have to look for possibly also complex instantons, objects that you would not consider for your physical observable.
So I think it's important here that we learn standard terminology. So is it standard to call this complex instantons?
I believe it's pretty standard, yes. Yeah, I think it's pretty good. Okay, so the point I want to make, yes.
Maybe I'm a bit lost with the logic. So maybe you can say a few words about how this Borel summability in quantum mechanics or quantum field theory is proven. And I'm not asking for more than a few sentences.
Yeah, well, I mean, this is, I will be glad to do this, but it requires a lot of work. Let me see if you will be satisfied with the few words I'm going to tell you now. So the few words I'm going to tell you now is that there is a procedure in which, in fact, Franz played a big role, which is called the exact WKB, which essentially started with André Voros, a colleague here, and others, okay, De La Bere, Dillinger, and Pam in particular. They did a great work during the 90s. So there is within quantum mechanics, using exact WKB, all this idea has been rigorously established. Again, it's essentially using resurgence, and at the moment I don't want to enter into this also because I want to postpone to another lecture. And all this has been proven. In particular, this large order behavior are now deduced rigorously, not with these tricks, but from some alien calculus, some sort of calculus that you can rigorously do, and using some other techniques, okay, in a completely rigorous way. This rigorous way of computing large order behavior, summability, and so on, as of today, is restricted to ordinary integrals and quantum mechanics. Okay. In quantum field theory,
it's not mysterious, and it's okay. I mean, we can imagine that we can establish large order behavior perturbation theory. I think the most mysterious thing is how then are we going to show that non-perturbative observable satisfies the conditions of this Nevanlena theorem that you give us. We should give some independent definition of the non-perturbative observable, like energy levels of quantum mechanics, and show that those things satisfies the conditions of the Nevanlena theorem. And that argument is not going to be based on this perturbation theory. It has to be based on something else.
Nevanlinia, I mean, I'm not doing a good job pedagogically. So the Nevanlinia theorem, as of today, is not very much used. In the sense that
you are wrong. I think all these people like Weidmann and others, I think they actually used this Nevanlena theorem.
Yeah, at that time, as of today, I said. As of today, unfortunately, this is not really used in the sense that proving for other theories then, aside from the class that I've been showed to you, the quartic scalar models, proving the applicability of Nevanlinia theorem is too hard. So people didn't do. Even a Dillinger within the exact WKB context, this has not been shown by using Nevanlinia theorem.
What can be shown?
The Borel summability of the enharmonic oscillator. The harmonic, this energy eigenvalues here, actually not only the ground state, but all the energy eigenvalues in the harmonic oscillator are, which has been proved by Weidmann et al. in the early 70s to be Borel summable to the exact results, have been proved by other means to all possible energy levels by other methods, which is exact WKB, which do not rely on Nevanlinia theorems, but use essentially more on the Stokes phenomena occurring in exact WKB. Okay, so as of today, unfortunately, Nevanlinia theorem is not very much of use because of the of its difficulty. On the other hand, okay, but again, I don't want to go into. we don't have a generic series. We have path integrals in our in the observable are given by a path integrals in quantum field theory. So you can sometimes you can avoid to use the linear theorem and use arguments basic on geometry. And using geometry, you have another way of proving Borel summability without bypassing the linear theorem. This is a nice story, which unfortunately I don't have time to review. In which I work personally, by the way, in which you can prove all of this from a geometric point of view by passing the linear theorem. Okay? The linear theorem is nice, but it's too hard to use it in general. So now coming to the Grisha also question, so you see that generically you have to go complex and you get the large order behavior, but sometimes you can have, as is known in quantum mechanics, you can have actual instantons. If you just study the double well, there is instant tunneling existing in quantum mechanics, in which case you do know that these actions are real. So in the double well, so if it's enough to change here the sign of this term here, you will get a double well, symmetric double well, in which instantons configuration enters, in which you know that there are non-perturbative contribution. An instanton is essentially a contribution of order e to the minus 1 over g. So e to the minus 1 over g does not admit any asymptotic expansion because it's 0 to all orders, right? So whenever you have real instantons meaning configuration, classical real configuration of Q with finite action, so Q is real, instantons, then Borel summability is lost. S0 in particular is greater than 0. You have a singularity, you get the same sign series, and you get indeed non-Borel resummable series, which from the point of view of the path integral are completely obvious. When you compute a path integral, you don't expect a single asymptotic series because you expect a sum over all possible saddles. Instantons are non-trivial saddles in the path integral. So if instantons do contribute, we expect to have one asymptotic series per each saddle. So whenever you are instantons, what do you expect? You expect that your observable will be a sum over an infinite number of asymptotic series, or what is called the trans series. Okay? So for the double well and real instantons, we go from series to trans series, which is very natural. Indeed, it's almost obvious. And we no longer, we lose forever the hope to compute, to Borel the sum of your system. Actually, there is a way to do it, but I don't want to enter into that. Okay. So if you do ordinary perturbation theory and you have real instantons, you are in the world of trans series, which is indeed the typical world of resurgence. So we are going to show you this, in the next lecture. Okay. So I don't know if I will be pretty brief, actually ultra brief on this part. So the main historical application, so one first historical application that people has been computing for many models, this large order behavior, refining this Lipatov trick and computing the A and C coefficient that I was telling you, and then computing a few orders in perturbation theory, and then attempting to do Borel resummation. So just to close a little bit this historical detour, the main application of all this has been, again, where the French school has been one of the dominant. The most relevant names are Brezen and Gijasten here in this business, and Leguillot as well. So the main application has been in computing a critical exponent in critical exponent in second order phase transition. So as you know, as of today, there are other methods, Monte Carlo and most of all the conformal bootstrap, which have superseded by several orders of magnitude the precision. So this is no longer say state of the art in terms of precision, but it played an important role historically, and as of today it can still be important whenever you want to know a specific RG flow, you know which theory you are studying, and you want to see what's going on. And so the main application has been very, very briefly. So one would have been in the so-called epsilon expansions. So the large order behavior of the epsilon expansions has been argued. Epsilon expansion is even more mysterious because it's even less rigorous than everything I'm telling you here, because epsilon expansion is necessarily perturbative, so you don't even know how to make it formal to rigorously have an idea on what you are doing. But anyhow, by using Lipatov trick, indeed Brezen, Leguilou, and Zijasen conjecture that this is Borel resummable for quartic scalar models. This indeed seems to be the case, numerically speaking. So people along the years, even today, they are computing a critical exponent by doing numerical Borel resummation of the epsilon expansion. Okay, and just to give you the idea of the numbers, although this is again it's superseded by other methods, the precision that you get is of order between 1% and 1 per mil, so not that bad. Okay, on the critical exponents. Typically, as again, most of the application has been doing in quartic scalar models, UN models, cubic models, other models, but in the realm of the scalar theories, in 3 dimensions and 2 dimensions. And also by doing another method, which has been developed, this method, of course, has been developed by Wilson and Fisher, the epsilon expansion, and then there is a little less known method developed by Parisi, in which you stay at your dimensionality, and you know that one of the great advantages of the epsilon expansion is that you stay away from infrared divergences because you exploit the good properties of a 4-dimensional theories in which you have under control infrared divergences. If you do a quantum field theory at criticality in 2 and 3 dimensions, you are plugged with infrared divergences, you go nowhere. So the idea of Parisi was to start with a massive theory in 2 or 3 dimensions at fixed dimensionality. Infrared divergences, of course, fixed by the mass, and then you flow to the massless critical case, starting from the massive flow. Okay. At the end of the day, this is another method, so I don't want to enter. I don't have time to enter into the details. At the end of the day, is a sort of similar to the epsilon expansion in terms of performances. So at the level of practical methods, you get more or less the same accuracy of order 1%, 1 per mil. The number of loops also has been computed more or less the same. I can only tell you from a mathematical point of view that this is slightly in a better shape, because the Borel summability here, you can rely on some rigorous proof of Borel summability, although there are a little bit of a caveats with the renormalization scheme. But anyhow, if you are just a pragmatic person that are, you focus on numerics, this might be better because the computation of loops here is easier because it's a massless theory. Here it's a massive theory, you need to compute numerically the loops. Okay. If you are a more formal guy, you might want to prefer this one because it's in a better formal framework. Okay, so do I have a few more minutes?
So did you finish the plan, or?
No, I didn't finish my plan. I had to still I had to talk about an important subject.
Well, I think.
How much time do we have?
To listen a bit more. Like, how much time do you think?
Well, maybe 10 minutes.
Yeah.
Okay, so I told you that there are a few models in which Borel summability has been proven, and indeed there is a very good reasons for this. The good reason is the following. So far we have seen that this large order behavior, this n factorial, were coming from other saddles. And this can be seen, these factorials, actually you see that it's the very same if I consider 0-dimensional integral, 1-dimensional integral that we have seen explicitly. If you you do the Lipatov trick in 2-dimension, 3-dimension, few things are going to change, the action, the equation of motion, but the essence of the idea is the same. This n factorial will come from this procedure here. And this is general. You can argue that this n factorial is simply coming from the fact that in terms of Feynman diagrams, you have a multiplicity, a factorial growth of the number of diagrams in your model. So this is universal. You can see also already in the ordinary integral. What changes when you change the dimensionality is simply the complicacy in computing the actual integrals of the Feynman diagrams. but the origin of the factorial actually comes from the fact that you have many diagrams. So if you wish, in a nutshell, we can say that this n factorial comes from, well, instantons, because we have seen complex instantons, because they are other saddle points nearby. In this sense, we can say complex instantons. And they are related from order 1 Feynman diagrams, so n factorial Feynman diagrams that you have to compute of order 1, each of order 1. This is a bit of a schematic. Please forgive me if it's a bit schematic, but just to... unfortunately, or fortunately, in some theories, there is a completely new effect which enters, which is much less understood, so it's very obscure, which is the following. In some theories, you can have order 1 Feynman diagrams of order n factorial. So this is a completely different phenomenon, has nothing to do with the factorial growth diagrams, it's simply with the fact that you can have this phenomenon. Whenever this phenomenon occurs in the Borel plane, you will have other singularities. Okay, so you have seen, maybe I didn't emphasize enough, but this -4 here, which was essentially the action, the value of this action, at the end of the day, if you remember, is the location of the Borel singularities of the singularities in the Borel plane. So the singularities in the Borel plane are in one-to-one correspondence with the action of the complex instanton. So you give me the action, and you know essentially where there is a singularity in the Borel plane. Okay, so in presence of this phenomena, there will be other singularities in the Borel plane that have nothing to do with instantons, which have been called renormalon singularities. Okay, so whatever you have this situation, we are in the we have a new character entering in the game, which are renormalon singularities.
I don't see the connection at all, because that was just the sum of all Feynman diagrams, and like if I have n factorial times 1 or 1 times n factorial, I just get the same n factorial, which is fine.
Yeah. At the end of the day, it's always an n factorial. I'm just telling you that in some theories, you can have in addition to this an additional factor which will come with its own factorial. This factor here will have a specific factor, and you will be able to disentangle one n factorial from the other. So there are ways to disentangle the two. In algebra 1, you are always getting an n factorial in front. What is the interest is to get the a to the n. The factor of a will tell you which singularity we are talking about. Here I'm simply saying that from the qualitative point of view, there is another source in some theories of behavior. So time is short, so I will be very brief. So in terms of Feynman diagrams, this kind of singularities come from a sort of chain of specific Feynman diagrams. So let me just show you the phi to the 4 in 4 dimensions, for instance. So for those of you that know quantum field theory, so I just showing here some Feynman diagram of a two-point function. This is an n-loop contribution, so these are n bubbles. And then there is a big loop. This is the two-point function with some momenta here. This is a contribution to the two-point function at loop level n. So now I'm going to argue that this sort of specific Feynman diagram is going to contribute with an n factorial, just one diagram. Okay. So yeah, maybe I will just, I don't have time to. So
this is a central concept for your lectures, with renormalon singularities.
Yes.
So it's a bit probably not very pedagogical to discuss it quickly now, because
Yeah, but the amount of time is finite, so I had to. Let me try to give, and then we can. You will tell me if this is good enough or not. So let me just. Yeah, to give you for an homework. So. So you see that despite this is an n loop, at the end of the day, it's relatively easy to compute this loop because this is an iteration of one loop. So once you compute this bubble, essentially this, and you iterate, you simply put to the power n, and then you have to do an actual one loop integral, which is the big integral here. Now the little loop integral, it's actually known because this is the truncated loop at one loop level, which is actually the correction to the one loop correction to the quartic coupling in the 5 to the 4 theory, which notoriously gives you the coefficient of the one loop beta function. So this plus the counter term that you need to add to make it finite, okay, this goes like beta 0 log of k over mu. Mu is the renormalization scale in quantum field theory. K is the external momenta into this loop. Okay, so this diagram here is going to be proportional to the number from integral from 0 to infinity in dk. K is the big loop here, is the big momentum entering of some f of k, and then what is important is that you are going to get a beta 0 from each of these bubble. You are going to get this factor here. Okay, so this is at the end. The result is already in radial coordinates in k, so this fk, it's a complicated function which I'm not going to write. So what is important for us?
Isn't it just to propagate the 1 over p minus k?
No, it's complicated because, as you know very well, you cannot do an integral actually in n loop without having renormalized the theory. So there are many counter terms. The story is a bit more complicated. I may sort of put it a lot of details under the carpet here, otherwise we will never finish. So at the end of the day, this is doing this integral properly is a bit of a complicated story, but at the end of the day you get this one, where this f of k, once you get it, you get all the UV divergences removed as the following property. So when k goes to 0, this goes like k to some coefficient AIR minus 1, so this is the definition of this AIR, it's going to be positive. And when this is the IR region of this integral, and when k is large, this is k to the a minus uv minus 1 with a uv plus greater than 0, so that this integral is converges both in the IR and the uv. So physically speaking, when k goes to infinity, you are looking at the short distance behavior of this big loop. If you wish, this big loop momentum space shrinks, and when k goes to 0, this is in physical space, becomes a very long distance effect. Okay, and now you rely on the following fact, that if I want to look at the region in the infrared, what is important of this integral is the integral from 0 to 1. So I can estimate the infrared tail of this integral to be given by this actual integral. So let me forget the mu also here. So this integral here is actually equal to n factorial minus beta 0 over AR to the power n times AIR. And similarly, the other integral, when you want to study the UV regime, let's cut it at 1 just for simplicity, and then this is going to be minus UV minus 1 beta 0 log of k to the power n, and this is going to be equal to n factorial beta 0 over a uv to the power n a uv to the inverse power. Okay, so now forget this factor here. What is the key point here is that you see that this single specific loop, because of the iteration of a log, essentially is and no matter what is this power AIR here, at the end of the day, it doesn't matter because you get an n factorial. So this IR is important because it's going to give you the factor of A, so this the coefficient in front, but the factorial comes automatically because you get a log. Now, so at the end of the day, then you will see that you are going to get new singularities in the Borel plane, whose location as usual depends on this factor. And this factor is equal to the one loop beta function coefficient divided by this A, This A is always positive by construction, and actually most of the cases, if you have a free theory, this is an integer. Not only it's positive, but it's a positive integer, whose dimensionality, whose actual number depend on the actual process you are computing, but it's an integer. So what really here, the sign of these factors depends crucially on the sign of the beta 0, of the one-loop beta function. So you see that you have two, in a theory you have at the same time both singularities. One is called the infrared renormalon, the one associated with the infrared. So the infrared renormalon is the singularity associated with this. And here we have what is called the UV renormalon. And now you see the bad feature is that no matter what is the sign of beta 0, one of these two is going to be on the positive axis, because we have a plus and minus here. So no matter what is beta 0, we are in trouble. So this phenomenon here, renormalon singularities, is the most dangerous and the problematic phenomenon in quantum field theory, which hinders a Borel summability of any perturbative theory. Okay, so
issue here. Why? Suppose I'm doing phi to the fourth theory in equal form. Why on earth would I extend my integrals to infinity? That's just, I would never do it. Because I know that my theory is going to have a Landau pole, so it's going to be some UV.
Yeah, good. Okay, so unfortunately, there are many comments that I'm trying to delete. So let's.
Worry about this.
Yeah, no, you should worry about this, because when you do computation in a theory, in quantum field theory, you typically integrate. We don't do a computer on a lattice, right? When you do perturbation theory, you want to renormalize, and then your integral in the dimensional regularization, you integrate over all possible k, for instance, over all possible momenta, right? You forget about the fact that the theory requires a UV completion. But indeed, you are right. What these renormalon singularities are telling you that this theory, secretly, but not so secret, actually are not well defined. So let me just, and then I will finish, let me open comment a little bit more on these two phenomena here. So you see that there are two cases. If beta 0 is greater than 0, then notoriously we have a theory with coupling is irrelevant in the infrared, which means it's a theory which flows at 0 coupling. This is a massless theory, by the way, massless. But as Slava was mentioning, it's very well known that this theory suffers from a Landau pole in the UV. Landau pole means that essentially the theory is at the non-perturbative level, it's actually non-perturbatively renormalizable. So the theory is, if you wish, is ill-defined. So the way in which perturbation theory signals to you that the theory is ill-defined is by showing to you that in the UV, in fact, you have a singularities over the positive real axis, which means that the Borel there is no way in which you can do a Borel resummation. Okay? This singularities is on the positive real axis. And this is fine. This is fine because it's on the negative real axis. Singularities in the negative real axis are fine, so as should be clear by now. I will comment a little bit more, but let me first contrast with the other case, which is also somehow interesting. When beta 0 is less than 0, as you know, we have in the situation like a QCD-like of a theory which develops strong coupling effect at large distances. Okay? So in this case, this phenomenon is okay. The theory indeed is well defined in the UV. This singularity is okay, but the issue is with the other one. This is again expected. We have a problem here at large distances, precisely where perturbation theory is supposed not to make any sense anymore, because as we know, the theory is strongly coupled. So the reasons why this name, which has been given by Toft long ago, renormalon, is, as you might see, this chain of graphs are precisely the one which contribute to what is called to the resummation of the leading logs, which is in the computation of the beta function. Indeed, beta 0 shows up, the one loop beta function coefficient. In other words, this phenomenon occurs anytime we have a running coupling constant. If you have a running coupling constant, you see that what does it mean having a perturbative expansion? You see that even asking what are we doing, mathematically speaking, doesn't make any sense, because you have to specify a scale. Then what does it mean having an expansion for small coupling if the coupling depends on the scale? it's obvious that at some point it doesn't make any sense. So coupling constant expansion from a mathematical point of view in the presence of running coupling is much more difficult, because we lose the notion of what does it mean doing a proper expansion. So proper expansion means you set a scale, you fix a scale, and then you decide that you do the expansion at that scale. But we do know that there exist large logs in quantum field theory, which indeed are these logs here, by the way, which are responsible for the breakdown in some situations of your theory. Not surprisingly, the breakdown in theories which have a Landau pole is in the UV, and not surprisingly, the breakdown is the infrared for theories which are indeed strongly coupled in the infrared. So the law, and this is still a law, I mean, we don't have any more justification, a common law, which I am part of which, I mean, I'm not, it's a good common law, okay, is that renormalons occur anytime occur for marginal couplings, classically marginal couplings. So if you think to the all the situation, all the list of models, 5 to the 4 kind of models that have been shown to you to be Borel resummable, the 5 to the 4 series for D3, 2, 1, and 0, these are theories in which all couplings were relevant couplings, so super renormalizable theories. We on purpose, we stayed away from marginal couplings, the reasons being that this phenomenon occurs, and this phenomenon does not allow any summability. Okay. So I have other comments to make, but probably I will postpone for the next week. Yes, please.
Okay.
Yeah, sorry. I think I will. A few comments more on next week, and I think I'm sorry if I went a bit over time. And yeah, that's the end.
Questions? Why does the resummation of the epsilon series work?
The resummation of the epsilon series works because it's literally below 4, and these renormal singularities do not apply.
But you are starting from some pervasive series from 4.
That's right, but then you rearrange it, and you stay always at the fixed point. At the fixed point, it's, I mean, this is a good point, which unfortunately is part of the comments that I will make next week. Essentially, since you flow at a CFT point, and you don't flow to a strongly coupled theories, this phenomenon do not occur anymore. Okay, both the UV and the IR.
Can I advance an explanation of why epsilon expansion converges?
Well, it does not converge, but it's resummable. Yeah, yeah.
Because the trouble with this procedure is that you are trying to expand observables in terms of coupling at a fixed scale. While in the epsilon expansion, you don't actually do this. You expand all observables in the coupling at the fixed point.
Yes.
Which is a very different thing to do.
Yes, yes. This is indeed the origin of the reasons. Yes.
But I wanted also to ask. I mean, it's true that the renormalons occur for marginal couplings, but they would probably occur in your theory when you were doing fixed dimension expansion if you insisted on setting the mass to 0. Because in that case, also, if you set the mass to 0, if you only have a cortical, because they're in 3D, all theorems about Borel summability that you quoted, they were only for massive theories. If you set mass to 0, then you have the same problem as in QCD. I mean, the theory becomes strongly coupled in the infrared, and we are not supposed to expect that you'll be able to compute all the physics in terms of.
No, there is a more serious problem if you consider a massless theories in, say, in 3 dimensions, that you are plugged with the power-like infrared divergences that you don't know how to deal with.
So the problem starts with.
Yeah. So. Yes.
Is there a similar story for large N expansion?
Oh, very good. So I will mention at the third lecture about large n. We know very little about large n expansions because they are very good at the beginning, at the leading order, but then they become very complicated. So we don't know much. I'm not aware if there is a sort of renormalon singularities for large n expansions. Certainly what is known is that, and in fact I'm going to show you, that the large n expansions are typically asymptotic with a Gevrey-1 asymptotic series. But the precise reasons of the singularities is, I don't think it's known generically.
I guess for exactly marginal couplings, I wouldn't expect any problems.
Yeah, indeed. Sorry, just another disclaimer. Let me make a disclaimer. So, in these theories, I'm consider generic quantum field theories. So there are many beautiful quantum field theories which are completely exceptional, which means if you have a supersymmetric theory with enough supercharges, meaning 8 supercharges in 4 dimensions, so from n equal to 2 higher, then renormalons simply disappear. The supersymmetry, there are magic, these are magic theories in which there is a lot of symmetries, which makes many things to disappear. So, as of today, I'm not aware of any renormalon singularities found in supersymmetric theories with n equal to 2 or more. So, certainly they do not occur for n equal to 4, for instance. Yes. So what I'm saying occurs for a generic quantum field theory.
But I think I wanted to be part of a more general statement that once you're on a conformal manifold at finite coupling, I would expect observables to be completely analytic. There's not even a need to be Borel.
Well, I mean, I think we have experts here. So I believe that in the computation of the anomalous dimension at large n, now I'm not an expert, so please, and in the audience can correct me. I don't know if this was your question. For the computation of the special anomalous dimension in n equal to 4, the series has been shown to be divergent. It's not analytic.
The Konishi anomalous dimension has, for example, in planar n equals 4, is analytic. There's finite radius of conversion.
No, but there is a no, but there is an issue here, Balt, that we are going to discuss in the third lecture, hopefully. Large n makes things completely different. Okay. At a large n, since again a very
But then even better. So when I'm not in the planar limit and I'm at finite coupling.
At finite n, the point is that I believe, at finite n, and then so not of coupling, you expand in G, then you should have still asymptotic behavior. And the reason is that the multiplicity
coupling also at finite G. So I'm on the conformal manifold, not at the free point, but I'm just
at any finite point, you are always analytic. So the issue is that the most dangerous point are always the free theory expansion, where you have an enhancement of symmetries because of higher spin and so on. It's always the most dangerous point. Right. If you are in the middle of a strong coupling expansion in quantum field theory are typically convergent.
Yeah, well, I didn't even mean strong coupling, just...
Yeah, sorry, then I'm with you.
There you have an exactly marginal coupling.
Yeah, I'm with you. If you expand... Yeah, this is what Thibault was asking. So if you expand, if you expand around an arbitrary value which is not 0, say positive coupling, then you typically are convergent. Because if you wish, it's a point of analyticity, so things should be convergent. And indeed...
Typically as if we know this. In fact, we don't know this, it's just a conjecture.
Well, when I say when I say typically, you are right. When I say typically,
don't know a single case where it has been shown.
No, there are. I mean, one of the cases in which this is shown and can be easily shown, it's indeed in the integrable theories I'm going to talk about in the last lecture. But I believe there are other cases in which this has been shown. If you wish, it's an expectation. Yeah. The expectation is what Bart was saying, which I believe it's a good common law. You don't expect a non-analyticity if you expand around an arbitrary finite coupling.
So you said you tried to, you estimated this behavior using complex incident terms, right? But what if there is some case where there are no complex incident terms, or can that then how this method will break down? But
yeah, this is a good question. So generically, if you remember, at least mathematically, when we said if we have a Gevrey-1 and I divide it by n factorial, you typically expect singularity somewhere. So they should be the singularities equal complex instantons in this language. So non-trivial saddle and complex instantons are essentially synonymous in my language. Okay, so typically you do expect. Indeed, there are situations in which you may not get it. I give you an instance. Q and D in 3 dimensions. Sorry, this is now a more physical question. Or you even, yeah, Q and D in 3 dimensions. So in 3 dimensions, you don't expect Q and D is super renormalizable. There are no running, so no renormalons should occur. So if any, you should have instantons or whatever complex instantons which tell you what is the large order behavior. But as a matter of fact, in QED, in 3 dimensions, we don't know of any instanton whatsoever. It's a fermionic theory. Which instantons are we talking about? And then the large order behavior is simply unknown. As of today, nobody knows. So there have been attempts long ago, again, Parisi, Berzen, Bogomolmi, there was various papers really more than 40 years ago, was inconclusive. So the only sort of apparent qualitative agreement was in the fact that the large order behavior is subfactorial. So it's a Gevrey fractional, 9 factorial to the power less than 1. The reason being that you don't have renormalons, okay? You have proliferation of Feynman diagrams, but since the loops are fermionic, you know that the fermion loops has a minus sign. So whenever you have many loops, you have in the Feynman at some given order, the loops cancel among each other. So there are large cancellation going on, and then instead of a usual n factorial growth, you get an effective subfactorial, whose precise factor, however, nobody knows. So in that case, if you do the direct Gevrey one, you divide by n factorial, you will get indeed a purely analytic all over the place function with some exponential behavior. But here, so you are right, there are cases of this kind, but it's a completely unknown territory. Nobody knows anything about it. We don't know a formal proof whether this theory should be Borel resummable, by the way, in principle. Nobody knows. Nobody knows the large order behavior. It's yeah, it would be good to understand better too.
How about scalar QED in 3 dimensions?
There, yeah, again, nobody knows, I believe.
But there, this argument about constellations doesn't apply.
Yes, doesn't apply,
So
but
there should be complex instances.
they should be complex instances. I don't know if anybody showed that, but there, you know, the argument is sit down and find this complex instanton. It's not easy to find complex instances, right? Because you are supposed to look over the possible complex plane, so it's hard because the function gets doubled. So you have instead of 1, you have 2 differential equation with the gauge fields. You have it's a mess. So nobody really did it. But the idea is that you will get it, and you will have n factorial because you don't have cancellations. So at least there is no. We understand more or less qualitatively.
Yeah, but but the connection. So if I just look at Feynman diagrams, indeed there are lots of diagrams, and maybe generically they just, don't cancel out. But then how do I see that this is connected to existence of complex instantons? I see both of them give you n factorial, but what's telling you that if you have like n factorial diagrams which don't cancel out, that means you have some complex instanton? Like, how are these two things?
I mean, okay, another little disclaimer. So this is an unexplored territory. So as of today, we know that there are 2 possible singularities in the Borel plane. There might be others, of course, that we don't know about. So I'm talking about this. The 2 that we know are these renormalon singularities. The law is that if you don't have marginal couplings, they are not there. And the other is proliferation of Feynman diagram. So we have to work under these assumptions because anything else can be there. Okay, under this assumption, QED3 doesn't have none of them, if you wish. Well, sorry, it can have proliferation, but say preliminary work long ago showed that there should be a subfactorial proliferation. That's what.
But that was fermion.
Fermion QED, yes.
Scalar QED, you still have.
Scalar QED, yeah. The idea is that there should be no cancellation. There should be an n factorial growth, and this will be governed by some complex instantons that nobody dare to compute, to find, because it's a complicated analysis.
So just to make sure, so you're saying it's an interesting question to make more precise the connection between complex instantons and proliferation of Feynman diagrams?
No, I'm not sure I'm saying that.
Is it a well-defined question?
I'm not really saying that because
is there something to be made precise here?
I mean, certainly at the level of quantum field theory, yes. And the reason is, I can tell you what is the key point. The key point is that I was a bit quick in this Lipatov trick, you select, you find a complex instance, and you include it, assuming that it contributes in the large order behavior. But actually, from both from the quantum mechanical rigorous result and from the integral, as I was telling you that you had to somehow sample these nearby saddle points, and not all of them contribute in the estimate. So only one in which some discontinuity, Stokes discontinuity applies. And what is the analog in the path integral? We really don't know. So if you wish, we don't know whenever you have a path integral, what are the saddles which we should integrate over. They are not all the possible saddles, certainly, but we don't even know what is the prescription. So mathematically, there is a prescription, which is Picard-Lefschetz theory, which gives us a prescription in principle for ordinary integrals, n-dimensional integral. But then for in the continuum limit of the path integral, nobody knows how to use it. So.
Any other questions?
I have a general question. So imagine I have some theory in which I know some observable to any given order perturbative expansion. Are you saying that this information is sufficient just to extract all non-perturbative information about the observable?
Well, this is at the end of the day the aim of these lectures. So, which is the aim? As you know, this is the ambition of Resurgence. So, I'm going to develop a lot of this. So, this is an excellent question, but I'm keeping for later. So, the answer is that at the moment there is no clue that this is going to work in general. I'm going to present to you an instance in integrable model in which it does. It does precisely. So if you know, you have to know, however, the whole series, unfortunately, perturbative series with, say, thousands or more. You have to know essentially the whole series. Then you can reconstruct all the rest. So this is a theory with renormalons, by the way. So I'm going to show you, maybe I should have told you, so I'm going to show you a successful theory in which you can have everything reconstructed with renormalons, starting from the perturbative series. This is not going to be Borel resummable because of this effect, but then analyzing this Stokes phenomenon, the fact that there are ambiguities, we can build up a transeries, and then at the end of the day, this transeries will indeed reconstruct the full exact answer that we know by thermodynamic Bethe ansatz. But in general, we don't know. I mean, typically, you see, unfortunately, the problem is that in order to do this, to check this program, you have to know much more than what we typically know.
Well, but sometimes if you're talking about more realistic serial like QCD, we know that the answer will be no, because first of all, you just give two examples, instantons and renormalons. And you know from different sources that if you're thinking about true nature of non-perturbative features in QCD, is not exhausted neither by instantons nor by the renormalons. There's much more complicated non-perturbative phenomena which contribute to observables, and those phenomena are not seen at the level of perturbative expansion. What I want to say is that
Like what?
condensate, gluon condensate, fermion condensate.
No, I mean, sorry, I mean,
your ground state.
This will one of the comments that I didn't have time to do, which is for the beginning of the second lecture. So there is a very nice, again, very historically well-established connection between renormalons and the OPE, which it's important I have to discuss next time, because it's so important that I don't want to rush on this point. So this correspondence, indeed, condensates appears, I mean, just to make the story short. So this phenomenon are the infrared singularities, sorry, these infrared renormalon singularities here are give you an ambiguity, which is e to the minus 1 over beta 0, which at the end of the day, with these factors here, matches the ambiguities due to condensates. In fact, in particular, Schiffman has been a great promoter of this correspondence between resurgence and OPE, I think he's right. So there is a correspondence here, and this is a nice way to see that condensate in QCD, a way to see condensate in QCD is a way to manage renormalons. The problem is that we know so few about renormalons that nothing can be done, can be established. Just to give you an example. At order n loops, so I have this diagram, and I have other n factorially growing diagrams. Who tells me what is the final combination of these diagrams? How can I study a single diagram by itself? It's completely unsystematic, right? So there is no way to establish anything in QCD.
Well, you said this is all related to beta 0. We know what beta 0 is.
Yeah, but I can have, since in a complicated theories, I can have other diagrams in which there may be some other cancellation as well, because in a theory in which you have a running coupling, you can have not because of renormalization. In the 5 to the 4 theories in lower dimensions, where the coupling essentially do not renormalize, you are essentially ensured that at loop order n, all the diagrams contribute with the same sign. In a theory where you have to subtract due to fixed divergences, this is not even true. You have different signs moving around, and you cannot even say that at the end of the day you will get, you might even get cancellations, so to say. So even more so with in QCD, where you have even ghosts, which are essentially fermionic particles, right? Have Grassmann nature. So we really don't have any idea. So again, this is for lecture 2. So the rigorous framework in which this renormalance has been nailed down in a systematic way, indeed even before our recent works were done by, again, one of your colleagues, François David, in which in the 80s he pointed out studying the nonlinear sigma model at large n. At large n in a vector theories, these bubbles are the leading large n results. So all the other diagrams are suppressed by 1 over n. So this is a clean framework in which you can address the problem. On top of it, everything is easier. You can compute things using large n techniques. And there, indeed, many things has been established in a sort of semi-rigorous way. Okay? But again, this will come later, because it's being integrable models, I will discuss within integrable models.
So it's the hope that all these larger order expansion series would capture all the non-pervasive physics somehow. Is that the hope, or?
I mean, I give you my honest answer. So my honest answer is that it seems so. At least, I mean, I was very skeptical when entering into this field, but I must say that things indeed seems to work, because this Stokes phenomenon, which is the kernel of everything, it's magic and powerful. The problem is practical, which means in practice how much this is going to be. So theoretically, it's a beautiful problem. It should be addressed, and it's great. Okay, but practically speaking, I'm not sure we will never get the proton mass doing some resurgence. Okay, so just rely on QCD or any other method, or on lattice QCD or any other, because the number of times that you need is gigantic, and with the current techniques there is simply no hope. So you see the distinction. If you want to do, if a series is Borel resummable, experience has shown that with less than 10 terms you get an excellent approximation of your observable at the level of per mil, with 7 or 8 terms. So, okay, you sit down with some patience, you compute 6, 7 loops, okay, or you ask experts to do for you, okay, and then you do decent work. But whenever you activate...
So we have a signal that the recording is going to stop soon, so you have to...
okay, no, okay, yeah.
Discussion.
Okay,
yeah. Somehow close
yeah, I will close with this. So whenever, however, you have a trans-series, so you want to activate this more ambitious program of resumming not a single asymptotic series, but an infinite number of 1, the precision that you need is huge, simply huge. So at the moment we can only check when it works. So I know the result already, and then I check that if I knew the asymptotic the perturbative only, I could reconstruct all the rest. So which is nice, but theoretically, because I already knew the result. So we are still at this stage of checking that the idea in principle works. My fear is that it's not really going to give you new results, because it's too hard. Unless you bypass the idea of doing trans-series and you change your series, and you are somehow, in a way or another, you are able to do to go in a single series Borel resummable. But that's, yeah, I mean, that's complicated.
Okay, so let's thank Marco and continue the session.